This lecture is about Kirchoff's laws, effective resistance, and equivalent circuits. Kirchoff has two laws. His law for currents essentially just says that what goes in must come out. In other words, at a junction in a circuit where we have some current I1 coming in and currents I2 and I3 going out, Kirchoff's law says that what goes in, I2, must be equal, what goes in, I1, must be equal to what goes out, that is I2 plus I3. Note that with each variable name for current, I1, I2, and I3, I defined a direction associated with that current, and it's really a sign convention. The way Kirchoff's law applies depends on that sign convention. So here there was I1 going in, I2 and I3 coming out. If instead I had defined these sign conventions with all of them going inward towards the junction, then Kirchoff's law just reads that what goes in, which is I1 plus I2 plus I3, equals what goes out, which is 0. Rearranging this, we get simply that I1 equals minus I2 minus I3. So we can see how this is the same as this equation, but with a minus sign applied to I2 and I3. So that's why the direction of these arrows really defines the sign convention for the currents. If you switch the direction of the arrow, that switches the sign in front of the current in Kirchoff's law. And there's nothing wrong with trying to solve a problem and coming up with a negative current. That just means that the actual current is opposite the direction of the arrow that we wrote in the diagram. Kirchoff's law for voltages says that the total change in voltage around any closed circuit is 0. For example, considering this simple circuit, if we consider going in a loop around this circuit and labeling the voltage of the battery V, the resistance of the resistor R, and the current I, then the total change in voltage around this circuit is plus V for the battery and minus IR, that's the voltage across the resistor, and Ohm's law tells us that that is I times R, V equals IR. So the total voltage around this loop has to be equal to 0 according to Kirchoff's laws. Now, note one thing, that the voltage across a resistor is a voltage drop. That is, the voltage goes from a higher amount before the resistor and then decreases as you pass through to the other side of the resistor. Now, because resistors carry voltage drops, it's for that reason that the voltage across a resistor appears with a minus sign when you're summing up the voltages around this loop. And this, of course, implies that in this simple circuit, IR, the voltage across the resistor, is just equal to the voltage in the battery. Now, as I noted before, the choice of the sign convention for I makes a difference. So if I had defined I to be the other way, then now the voltage across the resistor should appear with a plus sign. This is because the sign of, the sign of I is now reversed. The sign of I is now against the direction of the looping that we've chosen. So the loop goes this way through the resistor, but the current goes this way. So we should pick up an extra I sign, an extra minus sign, which cancels the minus sign that normally exists with a resistor. So that's why this is now V plus IR equals 0. This would imply that V equals minus IR, so if we were to go and calculate I, we would find that I is a negative number, and that's simply telling us that I is going in opposite the direction from where we chose our sign convention. That's all that means. Now, one last thing to note about Kirchoff's law for voltage, when we're talking about around any closed circuit, that's a loop and it has a direction. So here we chose these loops to be clockwise, but if we had chosen the loop to be the other way, how do we apply Kirchoff's law now? Well, now that we're going backwards, our loop goes backwards through the battery. We should see the battery as not a voltage increase, but a voltage drop. So it gives us minus V. And we're now going through the resistor, we're going opposite the direction of the current. So just as before, in this case where our loop was going opposite the direction of the current and the resistor came in with a plus sign, Here we're going opposite the direction of the current, and our resistor again comes in with a plus sign. So plus IR equals 0. And this is going to imply then, doing algebra, that V equals IR, the same as in the first case. So when we apply our loop in the opposite direction, it didn't change the result of Kirchoff's laws. We just have to make sure that whatever direction we assume for our loop in Kirchoff's law with voltages, that we apply it consistently to every element in that circuit, in this case, just the battery and the resistor. It's another sign convention. So when we reverse it, it reverses both signs, and this has no effect on the meaning of the equation overall. We just have to make sure that we apply that sign convention to every element in the circuit. Let's do an example problem to practice applying Kirchoff's laws. We'll call this V1 and this V2. And this will be R1, and this will be R2, and this will be R3. We should, so these will all be givens. We'll put some numbers in a moment, but not yet. First we'll work just with the symbols. We need to define sign conventions for our currents. So I'm going to call I1 going this way. I'm going to call I2 going this way. And I'm going to call I3 this way. Now let's apply Kirchoff's laws. We'll start by considering this clockwise loop. So starting here with the battery, what we get is V for the battery. We have a voltage drop from R1, so that's minus I1 R1. And then we have a voltage drop from R3 as well, so that's minus I3 R3. And this equals 0. Kirchoff's law for voltages applied to that loop. Now let's do this loop. Again, we'll go clockwise. We have, this was V1. We have now V2. And we have a voltage drop for the resistor, but look, the current is going the other way. So this is actually, we're going from the low side of the resistor to the high side. So this is actually a voltage gain in this resistor, plus I3 R3. Remember, this is dependent on how we defined our sign convention for I3. The fact that it's now going to the left, whereas our loop here is going to the right, means that we have to reverse what we normally do for resistors. So that's why it's a voltage gain instead of a voltage drop. And then for R2, our loop and our current convention are the same way. So that's a voltage drop as usual. I2 R2 equals 0. Now, it is interesting to note that there's a third loop we could consider in this circuit. Right? We could consider the whole entire loop going around the outer perimeter and not going through this middle part. What would we get if we consider this loop? This is what we would get. We would get V1 minus I1 R1 minus I2 R2 plus V2 when we come all the way back around. We hit V1, V2, R1, and R2. Now, this equation is actually redundant to these first two, because if I took these first two equations and just added them to each other, this is what I would get. I would get V1 plus V2 minus I1 R1 minus I2 R2, and the I3 R3 terms cancel out because one has a minus sign and one does not. So there is a third loop we can consider here, but it's actually redundant to the first two. It doesn't give us any new information, so we don't have to consider it. This is characteristic of applying Kirchoff's laws to circuits. Usually once you consider all the loops, all the possible loops, one of them turns out to just be redundant. Anyway, now let's consider the junctions. We'll do this junction right here. So this is Kirchoff's law for currents. It tells us that what goes in, I1, must equal what's coming out, which is I2 and I3. I1 goes in, I2 and I3 are coming out. Once again, we could consider this junction as well, but just like with the final loop we considered, it would wind up giving us information that was redundant. So normally oftentimes you find that you consider every possible loop and the last loop turns out to provide no information. Same with junctions. You can consider each junction. The last one turns out to give you no new information. Now let's solve for I3. I said the voltages and the resistors were givens. So I1, I2, I3 are unknown. I3 is the one we want to find, so I1 and I2 are nuisance variables, so we should get rid of them. If we look at this first equation, it's got an I1 in it. We can use this third equation to get rid of the I1, and then we can use the second equation, solve for I2, to get rid of the I2. Let's do it. First, I'll take the third equation and use it to replace I1 in the first equation. Okay, now I'll take the second equation and I'll solve for I2, and I'll use that to replace I2 in this equation down here. Oops, I forgot to note that this is V1 right here. And finally we have an equation which contains only known quantities and a single unknown, I3. So let's solve for I3 to get our answer. Oops, I just noticed a mistake. This plus sign should have been a minus sign. And there's our answer. Let's try putting in some numbers for the known variables and see what we get. Let's let V1 and V2 be equal at 1 volt, so both batteries are 1 volt. Let's let R1 and R3 both be 1 ohm. But then let's let R2 be a little more, 2 ohms. We then get that I3 is 1/5 plus 1/5 of an amp, so current is flowing to the left a little bit. But now let's consider another case. This time let's let R1 be the resistor with 2 ohms resistance, and R2 and R3 will have 1 ohm of resistance. We then get that I3 is minus 1/5 of an amp, so in that case current is flowing to the right. And this result we can actually make some intuitive sense of. In the first case, R1 was a bottleneck. Not very much current was able to get through, In the first case, R2 was 2 ohm resistor. So R2 is a bottleneck, very resistive. Current not able to get through. So current comes rushing through R1, and it finds there's not much room to get through R2, so the current says, okay, well, instead I'm going to go this way. It's going this way because there's not enough room for it to continue around this path. In the second case, R2 was the bottleneck. Okay, and R1 was a fairly open, relatively open path with a lower resistance, R2 is a relatively open path with a lower resistance of 1 ohm, whereas R1 was the bottleneck with 2 ohms. So current comes through here, but not very much, and there's actually more room for current to flow through R2, so it pulls current in from this battery this way through I3 to the right across this bridge in the middle. So that's why I3 comes out negative, because there's enough room for more current to come in and pass through R2, because there's not so much coming through R1. For homework, do a similar circuit. Given these voltages and these resistances, determine all 3 currents in the circuit, I1, I2, and I3. Now let's consider for a moment resistors connected in series. This means that the resistors are connected one after another, like this. Kirchoff's law tells us this, that the voltage is equal to the sum of the voltages across the 2 resistors given by Ohm's law, and this can be rewritten by factoring out the I. When we do this, this looks a lot like an equation for a single resistor. If we let that resistor have an effective resistance, we'll call it effective resistance R1 plus R2, then this just looks like V equals I, R effective. And here's the circuit associated with that equation. So what we've shown is that when we have 2 resistors connected in series, we can treat them effectively as one resistor, where the resistance of that effective resistor is the sum of the 2 resistances connected in series. So these resistors in series are equivalent to a single resistor with the sum of the 2 resistances. And that's pretty useful. What if we have resistors in parallel, that is, connected side by side? Kirchoff's laws applied to this circuit tell us this, Note that from one loop around the circuit, one that goes through R1, oh, whoops, I had mislabeled the currents I1 and I2, but now I fixed it. So one loop that goes through R1 tells us that this voltage has to be equal to I1 R1. That's this equality. But a loop that goes through I2 tells us that this voltage has to be also equal to I2 R2, so that's this second equality. And then Kirchoff's laws applied at either of the junctions would tell us this. A little algebra gives us this relationship between I3 and V. Calling this 1 over R effective, we reproduce Ohm's law for an equivalent circuit, just like before, except now the effective resistance is given by this equation. So this tells us how resistors in parallel add, different from how they add in series. So two resistors in parallel are equivalent to a single resistor with an effective resistance of 1 over the sum of 1 over R1 plus 1 over R2. Example problem, let's determine the effective resistance of this resistor network. The bottom two resistors are resistors in parallel that are equivalent to a single resistor with 6/5 of an ohm. How did I get that? Well, I used that 1 over R effective is equal to 1 over 2 plus 1 over 3. Okay, that's the 1 over 2 ohms for this guy, 1 over 3 ohms for this one. And 1/2 plus 1/3 is equal to 5/6. So R effective is equal to 6/5, and it's in ohms. Well, then we just have two resistors in series, and so we know we can add those two resistors in series, and the resistances just add to give 11/5 or 2.2 ohms. Note that I could not just add these two resistors in series, because they're not simply two resistors in series, there's another connection in between them. So it's not a simple case of two resistors in series and I just can't go adding them. These two, however, are in parallel, and I can add, so I can combine them, and then I have two resistors simply in series, and I can combine them to get this. So this resistor network has an effective resistance of 2.2 ohm. For homework, compute the effective resistance of this resistor network. Also, rank these four resistor networks from greatest resistance to least resistance. Assume that each resistor is the same. Just that these are all 1 ohm resistors. Finally, we're going to talk about equivalent circuits. Now, we've already seen some basic examples of equivalent circuits in the form of equivalent resistors, and we'll generalize these ideas now. Kirchoff's laws are really what tells us how a circuit behaves. So when we have two circuits, such as this one and this one, they're equivalent. So let the two resistors be the same. Okay, and basically the paths that we could consider around these circuits, we've got one here, and we've got one here. Now this circuit, we have a path here, and then we have an outer path, and this outer path is just like this path, and this inner path is just like this path, in that we would write exactly the same Kirchoff's laws. So put another way, in both cases we have a voltage supply with two paths that it can go through a single resistor. Here's one path it can go through a single resistor. Here's another path it can go through a single resistor. It doesn't matter that in this case the path goes left, and in this case the path goes right. They're both paths through one voltage or one battery and then a single resistor. So it doesn't matter which side we draw it on. So these circuits are equivalent. Let's consider another somewhat harder example. Here we're going to have a voltage, and current coming from that voltage hits a junction. Or really, I should say, a battery. And current from that battery hits a junction. So here we go. We've got a battery. Current hits a junction. On either side of that junction we have a resistor. We then have another resistor bridging across those two sides of that junction, those two paths. So here's that resistor. And then the two paths, well, they wrap back around to the negative end of the battery after passing through another resistor. So they each pass through another resistor and before connecting to the negative end of the battery. Let's do another example. From the battery we have a resistor and then a split, and each path goes through two more resistors before coming together again and going back to the battery. There's an equivalent circuit. Okay, so finally for homework, take these four circuits that I've given here. This is problems 5, 6, 7, and 8, and match them to the equivalent circuit over here on the right, A, B, C, and D. So for each 5, 6, 7, and 8, you should give one answer, A, B, C, or D. Note that some of these, two of these, may have the same answer. Okay, I didn't necessarily use each of these once, so there may be a case where one of these is the answer to two of these, in which case one of them wouldn't be used at all.